Algebra Centre. And I think it is this year all over the world. So now that's Atlantic Algebra Centre spread into UK. Okay, but for 30 years, Ottawa, and wrote a number of papers, wrote in 2 books. So this book was published in Techno spring of 1987, and quite recently, 2001, 2011, the book is closed. 2017? No. Oh, quite recent. Oh, yeah. That's good when 25 years end up with the right book written rather than share the entire. Okay, so he was did a lot of important work, you know, the area of non-associative algebras, Lie algebras, and that kind of business groups. This topic is devoted to the recent interest that is quadratic forms. Of course, quadratic forms appear in a lot of stories about non-associative algebras. Some non-associative algebras exactly defined using quadratic forms. So that's a very important business. Quadratic forms are often important backgrounds in many other areas of algebra. So, I want to you talk about quadratic forms.
Thank you very much, Yuri. Thank you very much for the kind invitation to talk here. As Yuri said, I'm a fan of the Atlantic Algebra Centre. Being conferences organized by the Atlantic Algebra Centre, and even here in St. John's, or at the train station, and recently in Harlem. So I should. So I will give you a course, mini course, an introduction to quadratic forms. And I should say that this is a course designed for graduate students, not supposed to know what is a quadratic form. So it's my apologies to the more mature mathematicians in the audience who probably know all that what I will have to say at least for today. Today's lecture will be mainly definitions we have to get off the ground somehow. But if you have a question, don't hesitate to ask me. You can interrupt me, or you can ask me after that. Okay, so let's get started. So I will start with the definition of what is a quadratic form. Okay. So a quadratic form, which I will abbreviate by a flat form. So this is a pair. Q, where V is the finite dimensional vector space. Over to the Q left. And Q is a map, goes from V to F, and it satisfies following 2 conditions. Number 1, Q of R times V is R squared, Q of V of R and F, V and V. And number 2, you can polarize a quadratic form Q, get a map of 2 variables, EQ, 1 goes from B plus E to F. And it is defined as follows. It is Q of B1 plus B2 minus Q of B1 minus Q of B2. This map of two variables is supposed to be R bilinear, if F bilinear. So this means it is linear in each variable. But by definition, it is also symmetric. So what does it mean what does this perhaps strange looking condition actually mean? Well, it means that quadratic form is a polynomial function which is quadratic as a polynomial. So let me explain this. Right, so suppose for simplicity, suppose that the dimension of V is 2, and suppose E1, E2 is a basis of V. Right? So then we can calculate that one or two these scalars. Then bring these negative terms to the other side and use your first condition. What it means is, what follows is that Q of R1 E1 plus R2 E2 is the same, is equal to R1 squared Q of 1 plus. Now this is R bilinear, so if R times 1, the R goes out. So this is R times 1, 2, B of 1, 2, plus R2 squared Q of E2. Okay. Now, what you should look at here is, you should look at this equation as follows. The Q of E1 are constants. This is a constant, this is a constant. And this as a function of R1 and R2, this is quadratic, right? There is no term of the form R1 to the 3, for example, right? Everything turns as quadratic. So I will leave it up to you to find the formula for a dimension of the similar formula. Exercise. It's nice exercise. Okay. So, basic assumption for this course is that not only are all vector spaces finite dimensional, something every first year student will like, but also I will assume throughout that F is a field of characteristic not two. Right, so this means that if 2R is 0, can divide by then R is. Okay. You can develop a theory of quadratic forms over arbitrary fields of arbitrary characteristic, but it is much more complicated in characteristic 2, and I would like to make my life easy, and so I assume throughout that field F has characteristic not 2. I will occasionally tell you this is a theorem which is true for characteristic 2, or I will tell you this is a theorem which is explicitly not true for characteristic 2. Okay. Right. Now, first thing I would like to discuss is the connection to bilinear forms. Right? You have heard perhaps the definition of a bilinear, symmetric bilinear form. Now, you see, this so-called polar form this is a bilinear form, which is symmetric. So what is the connection? Quadratic forms versus symmetric bilinear. Right. So if we have a quadratic form Q, then we can, by its very definition, we have associated to this quadratic form the symmetric bilinear form, polar, BQ. Okay? Now, if you look at the definition of BQ, you specialize V1 equal to V2 equal to V, what do you get? Well, BQ of V comma V is 2 V minus 2 times Q. Now, because Q has degree 2, 2 goes out, becomes a 4. And 4 minus 2, which gives you 2 Q. Okay. Now, therefore, because characteristic F is not 2, we can divide by the 2. And so we get that the quadratic form is a half times EQ. Right. So the symmetric quadratic form actually determines the quadratic form. Now, of course, you could say, well, then let's study symmetric bilinear form. Why do you insist on studying quadratic forms? Well, this is perhaps one is also interested in quadratic forms in characteristic 2, even more general quadratic forms, rings, or even more general quadratic forms over schemes. Some of you have heard schemes, no? Some. Okay. So this is why I use quadratic forms instead of symmetric bilinear forms. Symmetric bilinear forms in characteristic 2 are awful. If you can avoid it, avoid it. Study study symmetric bilinear forms in 2. Right. Now, of course, once you have a symmetric bilinear form, you cannot define not only this, but also you can simply take any symmetric bilinear form and you can associate to this a quadratic form by defining that this should be B of B comma B. And then you can associate it with symmetric quadratic form, a quadratic form. However, I call this not Q, but Q index B in order to indicate the dependence of Q. Now, if you take the polar form, B of index Q, B, right, the polar form in this sense, and this would be 2B. Therefore, you see again, you can only the bijection if you assume that 2 is right. examples. So we have seen already one example. Maybe we can associate to any symmetric bilinear form a quadratic form. So now let's look at dimension 1, right? The easiest possible dimension. Well, the first example, take any A, you basically F, and then define a quadratic form which universally is denoted by this symbol, A in it, goes from F to F, which maps an R to A times R squared. Right, so here A times R squared is the product with F. Now I claim that this is a quadratic form. So indeed, if you multiply the R by a scalar, it goes up to 2. If you calculate the polar form, then you will find that it is the following expression: R1 R2 is 2 times A R1 R2. As a function of R1 R2, this is bilingual. So we got. Okay. Now, there is a converse. If I have a quadratic form, on my base field F, then what you do is you look at the value of this quadratic form at 1, find A as Q of 1F, and then you see that Q is in fact just the quadratic form which I defined up. So this type of quadratic form gives you all quadratic form if your vector space has dimension 1. Next example. Well, suppose we have already 2 quadratic forms. Say we have V1, Q1, and into Q2. Quadratic forms. Okay. Then we can sum them. Namely, I define V as the vector space V1 plus V2. And I define what is denoted by Q1 per Q2. This is a function which goes from V1 plus V2 F, and it maps pair V1, V2, so little V1, little V2 is in capital V1 respectively. Maps this to Q of V1 plus Q1 of V1 plus Q2 of V2. So you can easily see that this satisfies the 2 defining properties of a quadratic form. So this is a new quadratic form. So I can produce new ones, and I can, of course, iterate this. So example 3. We have given several scalars, 1, n, f, then can, for every form, we scalar A1, we can, for look at the one-dimensional form. Verb to n, and this will be a quadratic form from the n-dimensional vector space. So this quadratic form has also a special notation. It's usually denoted in one n. Now, in more concrete terms, how does it look like? Well, so this quadratic form A1 up to AN. So if you evaluate it as a scalar and a vector at the end, I write the vector v as we should be on one line. Right, so there are high scalars. What does it do? How does it look like? Well, it's just A1 squared plus A2 2 squared plus n squared. So this is called a diagonal form. I will come back later on diagonalization. I will give you one more example that is useful. We have seen that you can add quadratic forms. Later, I will also multiply quadratic forms. Now, what is missing is multiplying at least by a scalar. Right? So, if you have a in f, you have 2 from b to f quadratic form, then you can scalar multiply. A times q is a quadratic form, maps the vector b, is obvious choice, A times q. So we can produce lots of quadratic forms, so we're not talking about the empty set. Okay. Now we know what are the objects. In order to form a nice category, I have to tell you what are the maps. Okay. So, isomorphs. Maps are called isomorphs. They are defined as follows. So given quadratic forms V1, Q1, and V2, Q2, our isometry, which goes from V1, Q1 to Q2, is vertical linear map by from two, such that you y5 from V1 then Q2, then you apply Q2. Yes, let's say that's Q1. So here's a picture. Here we have Q1, here we have Q2, two functions. Here we have 1, here we have 2, and here we have the map phi, which is supposed to be nice. This This is called symmetry. So in terms of elements of your vector space, what does it mean? I.e., right? I have Q1, V1 is the same as Q2, and then okay. So now suppose I have such an isometry. Of course, I can look at its inverse, and after all, this is a invertible linear map. So it has its inverse, which is also invertible. You will believe that. See it nicely from this diagram. First of all, we'll also make this diagram mu. You can always also compose isometries. Composition of an isometry is an isometry. And so if you specify that V1 should be equal to 2, V1 should be 2, then you get a group. This is called the orthogonal. Oh, Q. These are just all the group of all isometries from VQ itself. So this is an important truth for mathematics. We know a little bit about algebraic groups. These are the S points of an algebraic group. These are the groups which are used to describe certain important groups. Now I will use a symbol for isometry. Symbolically, I forgot to put it there. Just say there as we move this way. So this is my symbol for it.
If you're going to erase some.
It's okay. So, yes, we have a picture and you all have it memorized, but this is really fun, so I have to do it. Now, you may wonder, gee, certainly the identity is an orthogonal. It's an isometry, so lies in the sum proof. But are there in fact more than just the identity? Okay. So let me convince you that there are in fact easily more isometries. Example. So suppose you have say an X in B, which has the property that Q of X is not 0. Then I can write down that. Fine. Fine. R index X of B little b as B minus BQ BX QX inverse times x. Right here. Right? So first of all, because q of x is not zero, it is invertible. So this makes sense. Right? Now, because we fix the x, this expression is linear. Here we have v itself. So this is clearly an endomorphism of my vector space. And I claim, and that's one of the exercises, Rx like in the orthogonal group of Q. It's a very special orthogonal map. Maybe Rx squared is the identity of Q. Because of this, it is called a reflection. There are more in this exercise about this reflections. For example, you can look at all the submonoid generated by the reflection, and this will always be a normal subgroup of the orthogonal group. I'll come back to this later on. Give you another example of one, two. So okay. So suppose we have given quadratic form. And suppose I take a scalar a, which is of the form u squared, or u. The u is invertible. I will denote this as time, which is f 0. Then, because the u is invertible, so this means that d goes to u times d or not. So u is in scalar, u is a scalar, v is a vector. This is an invertible map.
Sorry, u squared equals to what?
I define this. Okay, we'll see later. Then to call this map phi. So what happens to calculate q of v times, right? So this is invertible map phi goes from v to v. It's invertible there. If you have q times v, this goes out. So we get u squared q of v, which I define as v. So you see, before I had defined scalar multiplication of a quadratic form by a scalar u. So this equation now tells you that q is isometric to a times q if a lies to square. Okay. So now to summarize what we have done so far, we have defined quadratic forms, we have examples, and we looked at the maps, the nice maps between quadratic forms. So, like, this is like in ring theory, when we find the ring, we find nice maps between rings, but essentially nobody studies rings abstract. So one needs classes of quadratic forms which are amenable to being studied. Where you can say something of interest, right? There is very little, well, there's one theorem one can say about quadratic forms. So the next topic then will be to define what is an interesting class of a quadratic form. These are what I call regular quadratic forms, sometimes they're also called non-degenerate. Yep. So like in group theory, this works by defining first a radical. So given a quadratic form, I define a radical of, in fact, of the echelon. So this quadratic form has polar form, the radical of the polar form is then all the b's in B such that in Q of B and everything in B is 0. Associated to any symmetric bilinear form, in particular to our polar form, is map, which is called the adjoint, which goes from the vector space V into its loop. Start, because these are just the F-linear map from the vector space V, the base field F. And it's defined quite naturally, namely you associate to a vector V the linear form which you get by taking yours. The bilinear form will do through then taking the second argument as your brother. Being a bilinear form means that if I fix one argument, it is a linear form in the second. So you have a well-defined map, and this is linear. Okay. See? And then this radical is just a kernel df. This map. Okay. So then we can prove semester exercise. But the following are FAE, the following are equivalent. Number one, this adjoint map is an isomorph. Well, number two, if it's an isomorphism, it is in particular effective. But 1 and 2 is equivalent because it's an exercise. Okay. I.e., what does this mean? Well, it means that this is injective, its kernel is 0. So, i.e., it has purely effect. Okay. Now, number three, there exists a basis B1 up to the n such that the so-called Corner matrix B2, EI, EJ, well, basis E1 up to En, so vector space has dimension n. So here Ij run from 1 to n. So this is an n times n matrix. Condition is that this matrix is invertible. Okay. Now, many years ago, invertible matrix was called a regular matrix. And so this is the reason why, one of the reasons why this is called a regular. Now, this is assuming for exist. This is also equivalent to following. In fact, for every basis, let's say E1 up to the n matrix, the ground matrix, EQ, EI, EJ. It's invertible. Right. And in this case, if all these four equivalent conditions are true, then Q is called regular. And this is my definition. Regular. Okay. So now examples. So
Is this from the input? If you,
it's called, I think it's called the Gram-Schmidt matrix. Right?
Wait.
Right. I'm sure. Okay. Now, I'd like to discuss one-dimensional case. Example one, given A and F, we have the one-dimensional form of F, which maps on I to A prime squared. We have seen that this is a quadratic form. Now, calculate this polar form and called P of R1 2 is 2A. So what is its radical? Well, for every R2, this is 0. This is 0, then it equals 1. So we get 2A of 1 is 0. But we can divide by 2 assumption. And so find out that the cases A could be 0, or A is not 0. So therefore, this form is regular exactly if A is not 0. Now, example 2. Suppose we have two quadratic forms. Then we have to find what is the sum. And sums. Okay. Now, exercise. Do1 as long as I do 2. So regular quadratic. If and only if do1 and 2 are closed. You should see this by calculating simply, right? What is the radical? Okay. Now, combine this, suppose theta a1 to a n in f, and we have to find the diagonal for it. And just n times the sum. Okay. So where is this regular? You apply this several times. This form is regular before its components are. In example 1, we have seen this one-dimensional form is regular if and so this is regular if and if on line are not zero. Okay. Now, remark. I told you that I would make remarks sometimes with this too. So what I have defined here, this works for any symmetric bilinear form, independent of the characteristics. And you can define regular symmetric bilinear form as if it comes from a quadratic forms on top. But then, if you look at the one-dimensional form, see this quadratic form is regular if and only if a is not zero, but we use that 2 is invertible. See, if 2 is not invertible, it's 0. And this is 0. Therefore, this particular form is not regular. So people didn't like that. And so they invented a generalization of regularity which works in characteristic 2. I'll talk about this. This is here. I'll talk about this tomorrow in the actual set. Okay. Now, let me go back to the radical. So the radical behaves, if this is not very nicely, it behaves like a radical should behave. Right? Think about ring theory. Have a radical, many radicals in ring theory. You want out the radical, get a new structure, new ring, and it's nice. So the same is true here. Example, PQ is arbitrary. Then the radical of PQ is the subspace. So I can follow its motion. So I can look V modulo vertical. And then I can define a map ratio F, namely a little v coset given by little v, so it's v plus vertical u. This should be mapped onto Q. Whole coset is mapped. Right? Our first thing and most complicated, this is well defined. Maybe I have to check this, it's well defined because you see, there could be another representative of this coset. I have to see that there is also a representative. This expression, this scalar is the same. So this is well defined. One. I notice y. And if you look at the radical of the bar defense, in other words, this Q bar is now a regular form. So we have kicked out all the bad stuff, and we have something which we hope we can study. We have now regular.
Said the regular quadratic form measure, not the regularity measure, but I do. So you said the regularity measure.
Well, you can approach it from different angles. You can say if the form is zero, this is not very interesting. Because the zero function is not very interesting itself. So you just model and get something which is regular. And now for the next 10 minutes, you have to believe, in 15 minutes, you have to believe me that regular is something we can deal with.
Can what?
We can study. We can prove something interesting. So the right? I said we can prove something interesting. So here is an interesting result. So there's a in the first non-trivial result, this mini course, is the Cantor-Dieudonné series. Both Cantor and Dieudonné are two important mathematicians of the 19th and 20th century, last century, which says the following. Suppose we have V Q is regular and the vector space has dimension n. Then every orthogonal transformation, that means phi of O of Q. O of Q, remember, was the orthogonal group. Every is a product of at most n reflections. So reflections, you remember, were a special form of orthogonal transformations. And what the Carta and Dionysium says, if the form is regular, then every element in this orthogonal group can be written as a closed n reflection. So this is the first non-trivial result. This is an important result that is used to define later on something that is spinal norms. And this is a result which is only true in characteristic, not true. This is not true in characteristic. There are exceptions. But never mind, don't worry, there are also means to make a further characteristic. Okay. Now, continue. I will now define special types of regular quadratic forms, so-called hyperbolic forms. Then we will see that regular form can be written as an orthogonal sum of hyperbolic form, something which is a nice problem.
So before you present it more, can you, is the reflection geometry interpretation, not just the name is come from the relation I squared identity?
Well, if the dimension of vector space is true, well, a reflection, it's a reflection in this hyperbole. You take the standard in the product, take the vector x here, and our x will reflect in this line. And the exercise says that this is true in general. There's a so-called hyperplane, namely the kernel of qx, and Rx is the reflection in this hyperplane.
So the line here, line is given by the.
Okay. So this is my x, then this is the. So this should be this is the right angle, right? So all of these are the vectors here are orthogonal to x, and Rx will reflect in this linear space.
So the V formula directly, V x is 0, then V is RV is V is V, and if V is equal to X, then RV X is equal to V.
That makes sense.
Thank you. Okay. So hyperbolic forms. So here, any vector space W, right? And all the vector spaces are finite dimensional in this course. But define U, right? On W direct some dual space into F of the same pair consisting of a vector little w and capital W, linear form should be mapped onto I. So this map is well defined as degree 2 if you multiply this vector by a scalar r. R times W, R times phi, so it becomes an R squared. And the height of W1 phi 1, W2 phi 2 is just phi 1 of W2 plus phi 2 W1. You can see that this is that by you can calculate its kernel. Right. So we get what is denoted by blackboard W, blackboard H of W. By definition, this is just W plus W star. And this particular so we have to find a quadratic form. And we have also defined the radical of a general quadratic form. So first inclination, whenever you see now a quadratic form, you want to see what is its radical. So radical right? You can see from this formula that it consists of all W phi such that psi of W is 0 for all psi and phi of V is 0 for all W. But obviously, if the phi vanishes on vector, the phi is 0. If you have a vector in a vector space such that all linear forms vanish on that vector, vector must be 0. So this is 0. So this is a regular quadratic form, very special regular form. You can see this also a different way that I calculated square matrix. Rather, we need to discuss what is thought. So, given any Q and any subspace U, one defines U per on the beam such that the polar form be this all of these. And this is a subspace of V. And an important fact is this exercise. If you have arbitrary VQ, then suppose that Q restricted to U is a regular point. And it follows that V is just U direct. Now, these hyperbolic forms can be characterized, I will come back to it, by saying they have a big space where the form vanishes. You see this hyperbolic form, look at the definition, the hyperbolic form on W itself is 0. Because if phi is 0, then you can see. So these are special type of spaces. Definition Q is called totally isotropic if and only Q of B is totally isotropic, Q of B is. Okay, let me. Suppose you have a quadratic. Suppose you have a subspace U. Then U is called totally isotropic. If and only if Q restricted to U is 0. So an example would be the subspace W in the hyperbolic. And one calls Q isotropic if and only if there exists a non-zero U in W such that U is totally isotropic, i.e. U is equal to 0.
So isotropic of Q and on U.
So, for example, quadratic form is isotropic if it contains a non-zero vector where the form vanishes. So, now, example, F. Right? So suppose that F is algebraically closed. And you have a quadratic form, which is at least 2. So then we get this quadratic form polynomial of degree 2 on a space which has at least dimension 2. So by the Hilbert-Nullstellensatz, since we know it has 0, means that then Q is proper. So this is just an example. Characteristics, factorized break close, there are lots of as a problem. So the last 4 minutes, I will tell you a little bit about the important work of somebody whose name is Witt and Smith. So quadratic forms have been studied since the antiquity. There are usually just results for specific fields. And it was Anne Smith who wrote what is nowadays called a single paper, less than 20 pages, and he completely revolutionized the theory of quadratic forms. He proved really spectacular results. And it had a tremendous impact on quadratic forms. So I will tell you one of these three important results. We'll come back to the answer later. And this is the width decomposition set. Okay. And it says the following. Every quadratic form PQ decomposes as follows. VQ is an orthogonal sum of a subspace totally isotropic. Something which is hyperbolic and something which is non-isotropic called anisotropic. There is totally isotropic. This is just the radical point. Qn is hyperbolic. In fact, it's a maximal hyperbolic subspace. And Vn Qn is anisotropic, and anisotropic means not as, meaning you cannot have a non-zero vector in this space where the quadratic form vanishes. For example, over the real numbers, every positive definite quadratic form is anisotropic. Moreover, this decomposition is unique up to isometry. So the justification for looking at regular forms, modding out the radical, it is at least partly here. You can mod out the radical, you get some, so this will be the radical, so you get something, this part is regular, then you decompose the regular part in something which is hyperbolic and something which is anisotropic. And as a follow-up, in lecture 3, I will just convince you, hopefully, that we won't study hyperbolic forms because they are not really very interesting. The interesting part lies here in anisotropic. Okay, so that's it for today. Tomorrow, not tomorrow, Wednesday, I will talk about phase change and, of course, some theorems of Schala and Springer and Minicourse. And lecture 3 will be on certain groups named after the questions.
Yes. So I just have one more question about the definition of totally isotropic. So does it mean given a subspace G, we say U is sorry, actually.
So
Okay, I mean, just add one sentence. This This is an old theory, and so sometimes the terminology is TG. So this is first part of the emphasis. You could simply say Q restricted to U is 0. But that's nice.
So which relation explain the name hyperbolic? I mean, with relation of the definition explains.
Well, it has to do with hyperbole. You look at the zero spaces. So if you have right, so they x equal to r, so v equal 2, then take the quadratic form, and form minus 1. This form is hyperbolic. And if you look at the level sets of this hyperbolic form, you get hyperbolic.
I heard about metabolic forms. How do they remain?
Okay. Metabolic form, hyperbolic form is the same in characteristic not 2. Hyperbolic forms can be defined in any characteristic. But in characteristic 2, metabolic forms are more general. So there are more hyperbolic. In essence, what you do is, so in the hyperbolic case, what you have is the vector space V is equal to W plus star. So let Q be Q form, and W star are totally isotropic. Okay. This is in hyperbolic. But in metabolic case, you also have, this is not necessarily totally isotropic. You can add bilinear form, which is bilinear form on W star. And the decomposition theorem is valid for characteristic not 2 and in characteristic not 2 and in characteristic 2, hyperbolic forms are not enough. You have to go to something more general called metabolic, so that
Something only on the star or on the.
Yeah, you can add a symmetric bilinear form on top of this.
Star, why?
Well, that's the definition.
Significant. Kind of significant.
You can, sure. You can add a symmetric bilinear form on W, but you have to have. So, given Given, so the theorem is the following. The result is the same. Given regular form and totally isotropic subspace W, which has half the dimension of V, then you can find complementary subspace such that in characteristic sigma 2, yes, so this is complementary, such that you get a hyperbolic space. But you cannot prove that you get a hyperbolic space in characteristic 2. Need metaphor. So you cannot get rid of the symmetric value of the form.
So just one more question. So could you repeat again how you use Hilbert's Walsh analysis to show the fact if the field is algebraically closed with the vector space, with the dimensional vector space is greater than or equal to, then Q is isomorphic. Yeah.
Well, because it has a zero. You have a polynomial.
So we can use any quadratic form as
So you can, so it goes. So the quadratic form, right? You constructed polynomial associated. So you choose a basis. The quadratic form will give you a polynomial function. From your vector space V, you basically. And this polynomial function has a zero. Not only if the dimension is big enough, zero is suitable for a hyperplane, so it has many zeros. In particular, it has at least one zero which is not zero itself.
Okay, thank you.
So this gives you an isotropic vector.
Thank you.
No question.
Right. Well done. So see you again.